Hello, everyone. Welcome to the second session on testing for specific domains. We will start with a short paper from Chidera Biringa, Automated User Experience Testing through Multidimensional Performance Impact Analysis. So go ahead, Chidera.
Hello, everyone. My name is Chidera Biringa, a final year master's student in computer and information science at the University of Massachusetts at Dartmouth. And my co-author's name is Dr. Gokanko, assistant professor in the computer and information science department at the University of Massachusetts at Dartmouth. I am presenting our paper titled Automated User Experience Testing Through Multidimensional Performance Impact Analysis. This research was funded by UMass Dartmouth Cybersecurity Center. Thank you all for your time and for your attention. This is an outline of my presentation. I am going to start by introducing automated user experience testing. Next, we talk about the problem statement. Then we look at the research question, methodology, the experimentation setup and results. We answer our research questions, and finally, we conclude. I would like to introduce automated user experience testing. User experience is the holistic experience or observational usability a user derives from interacting and communicating with the software. Automated user experience testing refers to the dynamic and automatic estimation of software usability. The problem statement. So these are two code snippets with a high similarity measure, and they perform the same task. The task they perform is to calculate the frequency of terms in a document. The fundamental difference between code snippets 1 and 2 is the way we accessed and manipulated the linked hash map. In code snippets 1, we accessed and manipulated the linked hash map using an entry set, whilst in code snippet 2, we accessed and manipulated the linked hash map using a key set. On a unit test level, code snippet 1 takes about 4 seconds to run, whilst code snippet 2 takes about 4 minutes to run. That is over a 6,000% increase in performance time. This might seem like a negligible difference, but if you deploy this inefficient code to multiple areas of your software, that results in a low-performing software, leading to a diminished user experience. And I anticipate software development teams wouldn't want that. So this is the problem that we're trying to solve. We have two primary research questions. Research question 1 is, can we develop a system capable of inferring the performance of pending updates in a software as a way of automated user experience testing? Research question 2, can our system provide software development teams concrete information about the time cost of the features to the user experience? These research questions will be addressed in the later slides. Our methodology consists of several components. I will quickly go over individual components. The first component is the collection and preparation of data. To build machine learning powered systems, it is imperative we collect data from the right source and appropriately mine that data. We collected our data from GitHub. We accessed the Git API and deployed the filtering program with specific parameters. First, we are analyzing Java software. Hence, the repo must be written in Java. Second, the repo must contain compilable code, i.e. complete code. Believe it or not, but the overwhelming majority of repositories in GitHub are usually redundant and are not appropriate candidates for any sort of rigorous experimentation. So this second parameter is very important for us. Third, remember we are attempting to infer the test performance of a software. Hence, the repo must have existing test cases present in them. It might be units, integration, system, end-to-end smoke test cases. What's paramount is that those test cases must be in the repository. Lastly, the repo must contain a considerable number of commits, stars, and contributors. Next, after deploying this filtering program, the repo is forked and cloned to our lab's Git profile. The next phase is the application of reverse engineering methods. We used Git commands to reverse the Git commit process of a software at a specific code state. So we want to get the code at specific times in the development lifecycle. First, we linked the local and remote repo using the git remote at origin command. Next, we use the git log command to log the commit sessions. All commits in GitHub have a unique commit hash value. So we log the repo and retrieve the hash value. We create branches using the git checkout branch command. These branches are where the repo versions will be housed. We push these branches to the remote repo. Finally, using the hash value gotten from our earlier step, we reset the repo to a specific point. After we deploy those branches to a Travis CI testing framework where the test cases are run and logged. The next component in the engineering of our source code features is the feature engineering component. Feature engineering, as you guys might know, is an important step in building the predictive components of intelligent systems. The performance of our system was heavily dependent on the influence of extracted features. To vectorize and extract features, we derive an extractor equation. The sigma from the I to the nth term is the number of feature occurrences in the source code. We divide that by the character length of the file and reduce the skew of the distribution by taking the log of the result. Now we know how to extract features. The next question usually is, how do we detect those features? We detect them by adopting co-telemetry analysis. Co-telemetry, in short, is how users read and write code. There are three dominant features in co-telemetry. Layer features. These features refer to the structure of a source code. Example, an author's preference for space over tabs. Lexical features refers to the semantic representation of a source code file. Syntactic features are programming language dependent and provide context on the programmer's style-based preferential characteristics present in the source code file. These features are extracted by applying our feature extractor equation and algorithm. The experimentation setup and result. The data used in our experiment consists of 13 input variables, 12 dependent and 1 dependent variable, 210 observations, 5 committed branches, and over 10,000 lines of code. The deployment of machine learning models was the final component of our research. This is done to evaluate how well our model performs. First, for our first experiment, to ascertain the best performing model, we deploy a pipeline of regression models. The random forest regressor was the best performing model with a cross-validated mean absolute error of 3.7. I need to note the reason why we chose mean absolute error as our evaluation metric. Mean absolute error does not consider the directional relationship between predicted and actual observations. It is only concerned with the absolute difference. Remember, the results of the test case might be minuscule. Commit 1 might have a test value of 11 seconds, whilst commit 2 might have a value of 12 seconds. Hence, we want to punish small errors over large errors. Our research answers. So if you remember, we had a couple of research questions at the beginning of the presentation. For research question 1, we were able to develop a machine learning powered system capable of inferring the performance of pending updates in the software as a way of automated user experience testing. So imagine the scenario. If you are a software manager in a company and you hire an intern to contribute to the production-ready software housed on GitHub. If the intern pushes this inefficient code through the repo, it automatically reduces the performance time of the software. So MPSS will serve as a buffer between the software developer and the primary code base. For research question 2, software development teams can make decisions about adding new features to the software by considering an increase in running time leading to a diminished user experience, which provides them with concrete information about the time cost features of the user experience. To conclude, we have investigated several source code representation and feature extraction methods. We created an integrated timer that consists of test framework for automated test cases and a reverse engineering method for identifying, selecting, and creating individual repo branches at specific commit point, and experimented with regression models to satisfy the predictive component of our methodology. However, while our results are promising, our scope for this paper is limited, and we are planning to expand our work in several directions. First, we acknowledge that the code base needs to have significant and carefully placed unit system and integration test cases for our system to collect timing data from. Hence, we want to reduce our methodology dependence on the availability of those test cases in the repo. Second, we plan to expand our raw data by including a wide variety of repositories from GitHub. Third, we intend to explore the application of deep neural networks that have a potential to yield higher accuracy, specifically a recurrent neural network, LSTM, due to the Git sequential nature of our data. Thank you very much for listening. I will take any questions now.
So thank you, Chi, for your very nice, very clear presentation. I was very happy to see a paper on user experience testing because that's my area, and I know it's a very hard thing to test, right?
Yeah.
How do you test user experience? The next paper also talks about games, and how do you know that a game player will have fun with it, right? So there are subjective things to test, and that's hard to do in an automated way. But there's a lot that has to be done in that area. So I thought, that this was a very clever way to, so what you are testing is performance, right?
Yeah.
Actually, but that you think it may correlate to user experience, and I thought, well, right, most of the time, that is true, but I wonder, it's something that I ask that your paper, had me think about. Do you think it's something that always correlates, that performance always will cause, a degrading user satisfaction?
I would not use the word always. I think we'd probably have a more robust and rigorous statistical estimation on the correlation between performance and user experience. But intuitively, for example, one of the reasons why I don't update most of the applications in my phone, especially when I was using an old model of iPhone, was because of the fact that I was very skeptical about what does update constitute. I have seen situations where I update my phone and I could accessing a particular operation in an application usually takes a few seconds, and whilst after the update it increases the performance. So that correlation is perhaps something we can do in further experimentation.
Right.
User experience has to do with usability, right? You need to know the usability of what you are testing. But what I would like to emphasize to your question is that we are telling the development teams that if you contribute this particular software feature, or if you commit this line of code to the primary code base, it will contribute this specific time to the overall performance of the software. So if the development team or the developer decides to go ahead with the commit, well, that is a decision that they would have to make. But we are giving you the time cost of the experience that you're going to get from contributing that code to the primary code base.
Right. That's why I think, yeah, it's a very clever thing. There's something else that you can add, to your knowledge. Some more data that it may influence if you commit or not. But yeah, I was also thinking about my mobile apps, and how do I I recently have to, in my home banking, now I have to configure like my biometric data, and it took me a long time, just to scan my ID, and but then the other things that went much faster. So now that all my biometric data is in my phone, I can do a money transfer very quickly. So sometimes, you add functionality to configure something first, but then, it makes the other functionality faster. So
Yes.
that's something you may want to consider. So I see some questions now. Rodrigo is saying, if I understand well, the best results were achieved by random forest.
Sí.